Welcome to this module. In this module, we will further look into the footprint metrics, and here we will focus on carbon footprint and water footprint. So, let us look at the carbon footprint. Carbon footprint is kind of a metric that is mostly related to the impact of human activities on the climate change. So, we are looking at mostly the emissions that are included in Kyoto Protocol that have contribution to the climate change or the global warming potential. So, some of the GHGs in Kyoto Protocol are carbon dioxide, methane, N2O and hydrofluorocarbons, and all results are represented in terms of CO2 equivalents. So, you will notice that this is not really a resource in terms of the such as land that we saw in last module, but this is more of CO2 cycle or the carbon cycle and how we are affecting the carbon cycle and the circulation of different emissions that have the global warming impact that is included in the calculation of carbon footprint. So, in terms of carbon footprint, this is what there has been this is what is included in calculation scope 1, scope 2 and scope 3. So, lot of businesses will talk about controlling or reduction of their scope 1 and scope 2 or also scope 3. And there is of course a lot more control on how they can reduce the scope 1 emissions, but scope 2 and scope 3 are sometimes beyond that controls that they can reduce emissions from. So, what is a scope 1? Scope 1 is anything that is the direct emissions from the activity, sector or product being considered. When we say direct emissions, that is something that is produced on site. So, emissions that are related, for example, by burning of fuel for heating requirement in a building. Similarly, burning of fuel in a boiler that is required on the site of the manufacturing plant is part of the scope 1. Similarly, driving a car which you are which is based on gasoline and is combusting the fuel to emit carbon, that is the scope 1 emission. Of course, it is easy to quantify this because we know the emissions factor for a lot of these fuel burning and we can know how much fuel is being consumed by tracking it, and that gives us an idea of how to get the scope 1 emissions. Scope 2 includes both direct and the emissions from the processes providing direct energy input. So, for example, if we have a process, it is burning some fuel to get heating, that is our scope 1 emission. But let us say that it also includes emission or it also consumes some electricity to run some machines, that includes the emissions from the electricity is our scope 2 emission, because the emissions, that electricity consumption on the facility is not producing any CO2, but we know that there is emissions that is produced in the production of electricity. So, that on-site electricity production generation or the emission factor of the electricity multiplied by the electricity consumption, that will form the scope 2 along with the scope 1 emission. Then scope 3 includes all the upstream indirect emissions included. So, for example, now let us see there is a process that consumes some fuel, but it also has some electricity consumption. So, that forms the scope 1 and scope 2, but then for the electricity production upstream, we might be requiring equipment generation or manufacturing of the cables and all of that. So, that all those indirect emissions, when we include that, that is our scope 3 emissions. When there is a discussion on reduction of the carbon footprint by a product or a company, they are mostly interested, they get lot of information on scope 1 and scope 2. The scope 3 is where it becomes a little murky to do the calculations. So, we will learn about the carbon footprint through a simple example. So, here this problem I have adapted from the textbook on sustainable engineering by Dr. Bhavik Bakshi. So, here we have the example on carbon footprint where there is a process which has following inputs. The process is consuming 5000 meter cube of natural gas which is burnt for heating. Then the process is supported by transportation of 10,000 kilometer using 10 kilometer per liter of gasoline. So, we are able to drive for 10 kilometer per liter of gasoline, and then it also has an electricity input of 10,000 kilowatt hour. So, here for the first 30 seconds focus on calculation of the scope 1 emission. The emission factor for natural gas is given as 1.922 kg CO2 per meter cube. Emission factor for gasoline is given as 2.32 kg CO2 per liter. So, take 30 seconds and let us just focus on calculation of the scope 1 carbon footprint for this process. Okay, so let us look at the scope 1 carbon footprint. So, by definition your scope 1 carbon footprint includes the direct emissions from combustion of fuels, okay, on site or for the support. So, here your direct emission will be, because the process includes natural gas. So, emissions from natural gas combustion plus emissions from transportation. So, natural gas being consumed is 5000 meter cube is being consumed, and the emission factor given is 1.922 kg CO2 per meter cube. So, that will give us the total CO2 plus the emissions from transportation. The transportation need is 10,000 kilometer and you are basically traveling 10 kilometers per liter. So, that will give us how much gasoline is being consumed, and then we multiply by the emission factor, which is the 2.32 kg CO2 per liter of gasoline combustion. So, that will give us the portion from the gasoline consumption. So, this is 9610 plus 2320, and that gives us a total of 11,930 kg CO2 equivalent of scope 1 carbon footprint. Okay. So, straightforward, when you have to calculate scope 1 carbon footprint, you know you want to collect data on the actual combustion of fuel on site or the emissions from direct transportation needs for that process, and all of that total summation gives you the scope 1 carbon footprint. Let us look at scope 2 carbon footprint. If you recall, the scope 2 carbon footprint is the total, that is the direct emissions plus the emissions that is produced for support of any other energy input. So, in this case the energy input additional is the electricity. So, scope 2 carbon footprint will include the scope 1 carbon footprint. So, I will write short for CF for carbon footprint plus the emissions from direct energy input. So, here of course, we have 11,930 plus emissions from electricity consumption. So, your electricity consumption here is given as 10,000 kilowatt hour. So, we have 10,000 kilowatt hour of electricity. Your emission factor is given as 300 kg CO2 per megawatt hour. So, we need to convert the kilowatt hour into megawatt hour. So, we divide by 1000 and that gives us that is equal to 14,930 kg CO2 equivalent of scope 2 carbon footprint. So, scope 2 carbon footprint is also very straightforward. You would want to know what is the direct energy input other than the fuel combustion that has been done directly at the facility or the transportation. So, that constitute the scope 1 carbon footprint. You calculate that separately, and then if there is additional energy input such as of electricity or any other input, you use the emission factor and multiply by the amount that is being consumed. So, here the process was consuming 10,000 kilowatt hour of electricity and the emission factor for electricity for that region is 300 kg CO2 per megawatt hour, and we convert the 10,000 kilowatt hour into megawatt hour and we get about 14,930 kg CO2 equivalent of scope 2 carbon footprint. Let us look at the scope 3 carbon footprint. Remember, scope 3 carbon footprint is about all the upstream life cycle emissions that are there to support that process. Now, in this case, we have three different inputs. We have natural gas, we have transportation needs which has the gasoline input, and we also have the electricity need. Now, when we are going to do the life cycle calculation for that, we would need to look at all the upstream processes that are supporting the natural gas production, gasoline production and electricity production. So, here in the problem, what you are provided is you are given the IO emission factor. So, if you remember, we have done the input output LCA where we can calculate the input output based emissions intensity or emission factor for any product from the economy. So, that captures the whole life cycle essence of production of that product. So, we have IO emission for natural gas is 2.43 kg CO2 per dollar, and you can see this is in terms of dollar because remember our input output model that we have seen is in the monetary terms. So, there is a natural gas production sector in the economy and that produces about 2.43 kg CO2 per dollar of your emission on the life cycle scale. So, now you can see that of course, it was 1.922 just for the direct one, but your emission factor that includes the life cycle all the upstream emission is 2.43 kg. Similarly, for electricity, we have 9.37 kg CO2 per dollar, and for gasoline we have 2.8 kg CO2 per dollar. Price of each of those are given. So, you can calculate what is the total dollar spent if the process is going to buy these products from the economy. So, remember our input output model, if that will be the delta F or that is the amount of dollars we need. So, we can multiply and know how much dollar is being used, and then we multiply by the emissions factor that are given at the life cycle scale to get the scope 3. So, let us look at that calculation. So, here we will add the scope 2 and then add all the upstream life cycle emissions. So, for that we will scope 2, if you remember, it was 14,930 kg CO2 equivalent, and for all the upstream we will use the IO based factors. So, let us look at each of the calculation for natural gas and so for natural gas, if you remember, if you have noted down, I would recommend that you have noted down from the previous slide that we have about 10 cents is the cost of the electricity of the natural gas. We are using 5,000 meter cube, and then that will give us the total amount of dollars spent on natural gas. So, this factor is giving us the dollars, 2.43 is the kg CO2 per dollar, and these two will give us the total dollars spent. So, that gives the total CO2 for This is for the natural gas input. Then let us look at the electricity. So, we have 4 cents spent on the electricity, and we have 10,000 kilowatt hour of electricity, and the factor is 9.37 kg CO2 per dollar. And then the last one is our gasoline. So, for gasoline we have $0.5, that is for per liter. We calculate the total amount of liters consumed. So, we have 10,000 kilometer and the mileage is 10 kilometer per liter, and that is then multiplied by 2.8 kg CO2 per dollar is the input output emission factor for gasoline. So, in this case this one is the electricity contribution and this is the gasoline contribution. So, remember that this portion already has the direct emissions from gasoline combustion and the transportation and also the direct emissions due to the electricity. Now, all these, this next part which we are calculating is the input output base. So, it is also calculating the upstream emissions from each of these processes. So, if you calculate all these values, this will come out to be 21,293 kg CO2 equivalent. So, remember, so let us write down our scope 1, scope 2 and scope 3 carbon footprint. So, scope 3 is 21,923 kg CO2 equivalent. Scope 2 is 14,930 kg CO2 equivalent, and then scope 1 was 11,930 kg CO2 equivalent. So, you can see that whenever we are calculating carbon footprint, when we start doing the scope 3 calculation, the carbon footprint significantly increases. So, if you are focusing on improving the carbon footprint of your product and process, you definitely need to also account for the scope 3. Most of the studies today very well cover the scope 1 and scope 2, but it is very hard to do the scope 3, hence because there is also the knowledge that is required where that product is being produced, what is the life cycle model for it, and that is where the LCA model becomes really relevant and important to develop a good LCA model to calculate all the upstream life cycle emissions for each of your input that will contribute to the scope 3 carbon footprint. Next, we will look into the water footprint.